Hello and welcome to yet another video of Cornerstones of Math. Today we are going to solve a geometry problem which is as follows. Triangle ABC is an equilateral triangle. Take an arbitrary point D on side BC, so this point right here is taken arbitrarily, and let E be the point where the extension of line segment AD meets the circumcircle of triangle ABC. Then we want to prove 1 over DE equals 1 over BE plus 1 over CE. I have indicated in the title that I'm going to show you two methods, so let's discuss these two methods. The first method does not rely on trigonometry, which is quite something I gotta say, because even though trigonometry can be very useful in many geometry problems, just using trigonometry again and again can be a bit boring. However, instead of not relying on trigonometry, this method involves drawing some additional lines in order to solve the problem, which are usually rather unintuitive and hard to think of. The second method is quite obvious at this point. It is the trigonometric method. This method has an advantage that we do not have to draw some magical additional lines that seem like coming out of nowhere. We can solve the problem using exactly what is presented in this figure right here. So let's get started. So first, a non-trigonometric method. Like I said, we need some additional lines, so let's draw these additional lines. First, we draw a line which is passing through point B and also parallel to line AD. So this is the first additional line, and we need one more. Second, we extend this line segment CE. Then these two additional lines will meet at a point outside the circumcircle, so let's call this point F. Now these two additional lines seem to come out of nowhere all of a sudden, which I partly agree. If I may provide a reason for these two lines, the relation that we want to prove is the length relation. And one way to obtain such length relation is by using similarities. And drawing these two lines is one way to obtain such similarity. But before we get to the similarity part, first we deal with some angles using the famous inscribed angle theorem of circles. First, this angle AEB is equal to this angle ACB because they are both inscribed angles of the arc AB. And since angle ACB is 60 degrees because ABC is an equilateral triangle, angle AEB is also 60 degrees. Next, also by the inscribed angle theorem, this angle AEC is equal to this angle ABC, which is 60 degrees. Therefore, angle AEC is also 60 degrees. Next, let's use the property of our additional line, which is that lines AE and BF are parallel. Then this angle EBF is equal to this angle AEB because they are alternate angles, hence angle EBF is 60 degrees. Moreover, this angle BFE is equal to this angle AEC because corresponding angles. So angle BFE is 60 degrees. Therefore, we arrive at the important conclusion that triangle BFE is an equilateral triangle. Hence, length BE, BF, and EF are all equal. This result will be used later on. And now the similarity part. More specifically, the similarity between triangles CBF and CDE. This means that the ratio BF to DE is equal to CF to CE. That is, this to this is equal to this to this. So we have BF times CE equals DE times CF. Here we can write this CF as CE plus EF. And now let's use the previous result, which came from the fact that triangle BFE is an equilateral triangle, hence BE equals BF equals EF. That is, instead of these BF and EF, we can use the length of BE. Then we have now BE times CE equals DE times CE plus now BE. So we have BE times CE equals DE times CE plus DE times BE. And if we divide both sides with BE times CE times DE, we have 1 over DE equals 1 over BE plus 1 over CE, which is the equality that we wanted to prove. Alright, now let's try the second method, the trigonometric method. More specifically, we are going to use the famous law of sines. Like I said, we don't need any additional lines here. But before applying this famous trigonometric law, we need to introduce some length and angle variables. As for length variables, let A be the side length of triangle ABC. This D is an arbitrary point on side BC, hence this length BD is a varying length. In that sense, let's use X for the length of BD. This gave this length DC as A minus X. As for angles, let angle BAD be alpha and angle CAD be beta. This means that alpha plus beta equals 60 degrees or beta equals 60 degrees minus alpha. So we actually need only one of them, but I'm still gonna use both alpha and beta in order to maintain simple notations. Then by the inscribed angle theorem, angle DCE is also alpha and angle DBE is also beta. Moreover, we have 60 degrees here and 60 degrees here. So also by the inscribed angle theorem, this angle is also 60 degrees and this angle is also 60 degrees. Then as for this angle BDE and also this angle ADC, by the exterior angle theorem, these angles are equal to 60 degrees plus alpha. Likewise, as for these angles ADB and CDE, their measures are 60 degrees plus beta each. These are pretty much everything we need in order to apply the law of sines. So now let's apply the law of sines. We actually have multiple triangles here. First, if we apply the law of sines on triangle BDE, then we have the length x, which is BD, divided by sine 60 degrees equals DE over sine beta equals BE over sine 60 degrees plus alpha. And let's move on to the triangle right next to it, triangle CDE. Applying the law of sines here gives length CD, which is a minus x, over sine 60 degrees equals DE over sine alpha equals CE over sine 60 degrees plus beta. But we have more triangles. We can also apply the law of sines on triangle ABD. Then we have A, length of AB, divided by sine 60 degrees plus beta equals x, length BD, divided by sine alpha equals length AD over sine 60 degrees. And finally, from triangle ACD, we have A over sine 60 degrees plus alpha equals A minus x over sine beta equals AD over sine 60 degrees. These are all we can get from the law of sines. So we have these, and let us take a look at first two equations. Equations 1 and 2 contain length BE, CE, and DE, which means that we can express BE and CE in terms of DE. We want to prove the relation involving 1 over BE plus 1 over CE. So let's express 1 over BE and 1 over CE in terms of DE. From equation 1, 1 over BE is equal to sine beta over sine 60 degrees plus alpha times 1 over DE. And from equation 2, 1 over CE is equal to sine alpha over sine 60 degrees plus beta times 1 over DE. So we have sine beta over sine 60 degrees plus alpha plus sine alpha over sine 60 degrees plus beta 1 over DE. Here, using equations 3 and 4, we can effectively simplify this part. From equation 3, you can find that sine alpha over sine 60 degree plus beta is equal to x over a. And from equation 4, you can find that sine beta over sine 60 degrees plus alpha is equal to a minus x over a. So we have this, which is just equal to 1 over dE. So we have obtained the desired equality. And that's all for today's video. Thank you all for watching. Please don't forget to hit that like and subscribe buttons if you enjoyed this video, and I will see you in another video.